In the concept, actually in 1980s, so some people proposed, so if we can put many electronic devices on the same chip, how about if we put so many photonic devices on the same chip? So this is the concept of photonic integrated circuits, and we also call it silicon photonics. Yeah. And the first people who proposed this idea is Richard Sorov. In about 40 years ago, and he is still around here. So we are very good friends. And after 14 years, silicon photonics is getting mature and mature. So actually, there are many advantages over electronics if you can use photonics. So the first one is carrier. For electronics, we use electrons or holes as the carrier. But either electrons or holes has mass, so it has limited velocity. But if we can use photon is light, so the speed is very high. And so the data transportation rate can be very high. And the second one is bandwidth. For typical electronics, if you can achieve a bandwidth of 10 gigahertz, it's already very fast. But for photonics, it's possible to achieve 100 gigahertz. And for energy consumption, so due to the heating effect, so electronics have some issue about energy efficiency. And for photonics, actually the required energy is much smaller. And also we have thermal heating issue in electronics. And for photonics, we don't have much thermal heating effect. And for electronics, we also have EM disturbance, but for photonics, it's not very much. And for body, electronics is larger, and for photonics is smaller. Yeah. So based on those unique advantages, so nowadays people in the field of photonics are trying to develop this kind of integrated photonic circuit technologies. And here is one example for photonic integrated circuit. So actually, people are using this kind of technology every day, like for the camera in your phone. So actually, in 2017, Sony proposed a 3-layer stack CMOS image sensor technology. So this is the structure. So on the top, they have photodetectors arrays, so which you can capture images. And in the between layers, a DRAM layer, so they can store those information. At the bottom, they have logic circuit and real circuit, so they can process the data. So you can see this kind of device actually integrate photonic component and electronic component on the same chip. So actually they can fabricate in a modern CMOS foundry with very high density and a very low cost. So everyone are actually using this kind of sensing element every day. So it's very powerful. Okay, so actually if we take a look of the development of silicon electronics, from the invention of first transistor to the modern electronic devices we have is about 15 years. So we believe using silicon photonics technology, we can also reduce those bulky photonic devices into a very small chip for many useful and powerful applications. So we believe silicon electronics has changed the world, and we believe in the near future, silicon photonics will change the world. And the market of silicon photonics is actually growing very, very fast. and in different area like data center, long-haul transceivers, optical interconnections, LiDAR, and some biosensing and fiber optical gyroscope. And actually, the increasing rate is about more than 10% every year. Yeah, so actually, it's a very fast-growing market. And talking about integrate photonics, some people will say, okay, it's not necessary to be on silicon. So actually, there are three main different platforms for integrate photonics. One is silicon, the other is III-V on silicon or indium phosphide platform. So for the three different platforms, actually they have their own advantages and disadvantages. But if we consider the cost, actually the money, no matter material cost or fabrication cost, actually silicon technology can beat everything. Yeah, so eventually we prefer integrate photonics to be on silicon rather on other platforms. So currently the key research topic in silicon photonics is including several research areas. So the first one is to develop fundamental building block like light source, waveguide, modulators, photodetectors, and local assemble and integration. And on this research area, actually, many research are working on materials and devices. So after we have those building blocks, then we can try to build a real product. So then we can send our materials and design an integrated circuit and realize it in the modern foundry. So for our research area, actually we are working on this area. So we are trying to develop materials and devices for silicon photonics. Okay, but actually it's very difficult to develop active photonic devices on silicon using grooveful materials. So this is the periodic table. If you take a look at column 4 element, currently we already have silicon and germanium in our chips. But if you take a look at the base structure of the silicon and the germanium, so both of them are in direct bandgap material. So which means the conduction minima and the valence band maxima are not located at the same K point. So you cannot have a direct transition. So this gives us very significant limitation on the devices. For light emitters, so because we cannot have direct transition, so the emission efficiency is very weak. So sometimes we are just joking. So silicon is a dark material because it cannot emit any light, and it also cannot have efficient optical modulation mechanism because due to there is no efficient electro-optical effect due to the crystalline symmetry. And for photodetector is the same because the direct bandgap transition is prohibited. So the absorption is very weak. So for example, for silicon solar cell, silicon is also a direct bandgap material. So the absorption coefficient is not very high. So you need to make your absorption layer very thick to fully absorb the coming photons. Yeah. So it's necessary to develop those three building blocks to complete silicon photonic chips. Okay, so the opportunities to use a new material system, silicon germanium tin. So if you take a look at the column 4 element, in addition to carbon, silicon, germanium, so there is another element, tin. So tin actually is for tin it has two types. So at low temperature below 286 K is alpha tin. So alpha tin is actually a semiconductor, and the higher than 286 K is beta tin. So it's a metal. So this is the material you use when you welding something. Yeah. So it's a very common material. So if we can introduce alpha tin into silicon and germanium, so actually we can create a new class of group 4 semiconductors, including germanium tin, silicon tin, and the silicon germanium tin. So what advantage we can have if we can introduce tin into silicon and germanium? So this is a very basic diagram for compound semiconductors. So the vertical axis is bandgap energy. The horizontal axis is lattice constant. So silicon is here, germanium is here, and actually for tin, the lattice constant of tin is very huge. So for silicon germanium tin material system, actually it spans a very wide range of lattice constant. So actually it can and it almost covers many different types of 3-5 semiconductor compounds. So it can use as a buffer layer to develop a new heterostructure like solar cells. And also by adjusting the composition of silicon, germanium, and tin, we can also have a very wide range bandgap energy tunability. So you can tune the bandgap energy. So actually, if we can have a tin in silicon and germanium, it offers many useful advantages. So another interesting for silicon germanium tin material system is if we can add a tin into germanium, so we can actually transfer the material into direct bandgap material. So for pure germanium, so you can see the direct conduction band is here, indirect conduction band is here, and their energy difference is actually very small, just 136 millielectron volt. And for tin, actually is a negative bandgap material, so its conduction band lies below the valence band. So if we can add a tin into germanium, actually the energy difference will be reduced, yeah, just like this. So if we can add more and more tin into germanium, so the energy difference between direct and indirect conduction band will become smaller and smaller. So if you can have a tin composition around 6%, so the direct conduction band can be lower than the indirect conduction band. So the material becomes a truly direct bandgap material. So using this property, we are trying to develop germanium tin lasers. Yeah, so we are trying to make germanium tin emit light. Okay, so actually for my research group, actually we are working on silicon germanium tin materials and the devices. So first of all, we are trying to grow these silicon germanium tin materials using molecular beam epitaxy. And when we have the material, we are trying to develop 3 different types of active devices, including light emitters, optical modulators, and the photodetectors. Okay. So for the operation range of silicon germanium tin devices, actually you are trying to push the range from near infrared to mid IR. So for conventional silicon germanium based photonic devices, the operation range is actually is mostly in the range of near IR, from about 0.7 micron to about 1.4 micron. So we are trying to extend application range for group 4 devices to short wave infrared or even mid IR. Okay. by doing so, actually there are more very new and exciting applications, like a long-range LiDAR sensing. So this will be equipped in every in your car in the near future. Okay, and like for biosensing and quantum computing, and there's a new window for communications. We call it 2-micron band fiber optical communication, and also thermal vision. So we call it the near-infrared silicon photonics. Okay, so introducing tin into germanium is not a new idea. It was proposed like 30 years ago. But what some people may ask, how come there's an idea 30 years ago, but it just realized in recent years? Because this material is not easy to grow. So this figure shows the phase diagram of germanium and the tin. So actually the solid equilibrium stability of tin in germanium is only about 2%. So which means in thermal equilibrium state, you cannot have too many tin in germanium. So if you have too many tin atoms in germanium, what happens? The first one is those tin atoms will tend to segregate to the surface. The second one is those tin atoms will form cluster in the materials. So actually it's very difficult to grow high quality and the high tin content germanium tin layers. The second challenge is lattice constant mismatch. So if you take a look of the lattice constant of germanium and the silicon, the lattice mismatch is already 4.2%. So actually it's already very difficult to directly grow germanium on silicon. So people have tried to grow germanium on silicon directly, but it takes about 20 years to be able to grow good germanium layer on silicon. But if we would like to introduce tin into germanium, actually the lattice constant mismatch is even larger. So it's more difficult to directly grow germanium tin on silicon. Okay, so how we try to address this challenge? The first one is we grow a germanium tin layer using molecular beam epitaxy at a very low temperature. Now, because as what I just said, in thermal equilibrium state, tin atoms tend to run away from germanium. So how we can grow high tin content layer in germanium tin? So we are trying to grow it using non-equilibrium conditions. So actually we are trying to grow the material at a very low temperature, around 80 to 150 degrees C. So the growth temperature is very low. For pure germanium, the typical growth temperature is like 500 degrees C or higher. For germanium tin, it's just like 80 to 150. So sometimes I will joke to my students, the growth temperature and your coffee, do you know which one is hotter? It's similar, because for good coffee, the temperature is 92 degrees, and for our growth temperature is only about 100. Yeah. And in our MBE chamber, we have silicon, germanium, and the tin, and also we have efficient cells for boron and antimony. So for P-type and N-type doping. So actually we can do in situ N-type and P-type doping. So in other words, we can grow many different kind of heterostructure using our MBE. And about the challenge for lattice mismatch. So in early years, people directly grow germanium on silicon wafers. The advantage is the first one is the cost is very low and it's CMOS compatible. But due to the lattice mismatch, so you can see those layers are very defective. So material quality is very poor. So how we can address this challenge? So we propose before we grow germanium, we grow a germanium buffer layer first. So firstly, by growing a germanium buffer layer, we can localize mismatch dislocation near the interface between silicon and the germanium. So at the top, actually, we have a very high quality service, and then we grow our germanium active layer. So in this way, we can improve the quality of germanium layer. But there is one disadvantage, which is those germanium layer will be pseudomorphic on the germanium buffer layer. So there is a compressive strain in the germanium layer. Okay, so here are some samples we grow using our MPE. So actually, we can grow germanium samples and even quantum wells, because for MPE you can have atomic layers thickness control, and we can also grow like a very typical PIN structure, and we also grow like PN, IN phototransistor structures. Okay, so then I will share our some research result on high performance germanium mid-infrared photodetector. Okay, so actually mid-infrared sensing system is very important, especially for military applications. Like in F-35 fighter, so actually it equipped this kind of night vision system in F-35 fighters. So even in a very dark environment, the pilot can see everything. But this kind of system is very expensive. Currently, most of this kind of system is based on Type 2 superlattice, and but for this one, it's very expensive. So if my memory is correct, I think only for this system, the price may be like several million USD dollar. So it's very expensive. And also, if you have experience on using some infrared camera, it's also expensive. Like for this one, the price is like 5 million NTD for mid-infrared camera. Okay, but actually they are challenging for developing mid-infrared photodetectors. So for the choice of materials, actually there are two categories. The first one is group 4, SeGn germanium-based photodetectors. So the advantage is CMOS compatible, and so you can easily integrate it with circuits. But the problem is this figure shows the quantum efficient spectrum for different materials. So actually you can see for silicon is the green one and the germanium is the orange one. Actually the cutoff wavelength is around 1.1 and 1.5 micron. So actually silicon germanium photodetector cannot detect mid-infrared light. For another category is 3-5 photodetectors like InGaze or antimony. So they have very good mid-infrared detection efficiency, but actually they are not CMOS compatible. So how people can make a mid-infrared imaging system using 3-5 photodetectors? So they need to do photodetectors array and real circuit separately, and then combine it together using wafer bonding. So actually, but for the alignment, it's very difficult. So actually, the yield is not very good. So this is the reason why 3-5 mid-infrared imaging system is so expensive. So here we are trying to address the challenge. So can we have mid-infrared sensing capacity and the CMOS compatibility at the same time? So actually, our Group 4 silicon germanium material systems provide this opportunity. So this figure shows the absorption coefficient spectrum for germanium and the germanium. And as you can see here, for pure germanium, the cutoff wavelength is around 1.5 micrometer. And if we can add a thing into germanium, actually the bandgap energy is become smaller. So what kind of advantage we can have if we can make the bandgap energy smaller? So the first one is, you can see we can extend the photo detection range. So we can have a wider photo detection range in the mid-infrared. The second one is, if you fix at a wavelength, you can see the absorption coefficient is also increased. So at the same time, we can enhance the quantum efficiency. Okay, so the first germanium photo detector was reported in 2009 by a team in Arizona State University. And after that, people are trying to develop different type of germanium photo detectors. And for development of photo detectors, there are many different criteria, like wider. So here we are focusing on a wider photo detection range. So if we can introduce more thing or introduce strange engineering, we can make the photo detection range wider to cover more mid-infrared range. The second one is higher responsivity. So here we try to use resonant cavity or photo transistor to enhance the responsivity, or we say it is a sensitivity. And reducing darker and the noise is also very important. So here we are trying to use quantum wave structure to lower the darker density or lower the noise. Then another important thing is operation speed, but this may not be necessary depending on your application. So some people have tried to push the operation speed to like 30 gigahertz. So we are trying to develop different kind of germanium photo detector to meet the requirements of good photo detectors. And this is our first generation germanium photo detectors reported like almost 10 years ago. So for this work, we developed a normal incidence. We developed a normal incidence. For this work, we developed a normal incidence germanium photo detectors. So we grow our materials on we grow our germanium layer on the germanium buffer layer first, so we can confine the defect at the interface of germanium and silicon layer. So the material quality in our germanium layers actually improve. So here we grow 3 samples with different content from 0%, 1.78%, and 3.85%. And this figure shows the responsivity spectrum for the devices. So for the pure germanium sample, so as you can see, the cutoff wavelength is around 1.5 micrometer. And with the increase of tin content, actually we can see the responsivity curve shift to longer wavelengths. So actually we can extend the photo detection range of the photodetector. And for the sample with 3.85% tin, so the cutoff wavelength has been extended to 1.8 micrometer. So these devices can actually cover the entire telecommunication band, so which is typically from 1.26 micron to 1.67 micron. So our devices are very useful for fiber optic telecommunications. And at the same time, we can see the photo detection responsibility is also enhanced. So actually, germanium photo detectors can have better sensitivities than germanium photo detector. But one problem for germanium photo detectors is backcurrent, because when we reduce the bandgap energy, actually the backcurrent also increase. So for germanium photo detector, as you can see here, when we increase the tin content, the backcurrent also increase significantly. So we are thinking about, okay, so what is the problem to induce dark current? So one problem is when we grow germanium tin on germanium, and when we increase the tin content, so the lattice mismatch between germanium tin and the germanium is will become larger. So when the thickness is larger than critical thickness, actually defect will generate and induce strength relaxation. So this is one of the main source for dark current. It's because it's due to defect-related dark current. Then we are thinking about, okay, so how we can reduce the defect density. So we propose instead of growing thick germanium tin layer, we can grow germanium tin quantum well. So because for quantum well, the thickness can be very small, so we can control it to about 10 nanometer. So it can be well below the critical thickness. Then in this way, we can suppress the generation of defects. Then we grow a germanium quantum well structure with 5 pairs of quantum well, and the barrier is germanium, and make germanium waveguide photodetectors. So as how we can expect, the backcurrent density at -1 volt is just about 59 milliampere per centimeter squared. So this value is almost the best in 2017, and the typical value before that is around 1000. So using the quantum well structure, we can suppress the backcurrent density by a factor of about 20. And then for photonic integrated circuit, actually instead of normal instance photodetector, actually we prefer planar photodetectors because it can easily to integrate and communicate with other photonic devices. So we are also trying to develop germanium waveguide photodetectors. And this is our first work published in 2014, and after that we also developed different generation of photodetectors. And this is one work we just published this year. So we have pushed the tin content to about 6%. So the bandgap energy has been reduced to about 0.55 electron volt. So we can extend the photo detection range to about 2000 nanometer, and the cutoff is around 2.2 micron. So actually we can cover the entire telecommunication band, and we can also cover one of the new emerging 2 micron wavelength band. So this device can be very useful for 2 micron band communication. And our work is selected as the back cover of this widely journal, Advanced Photonics Research. And for the responsibility, because for waveguide photodetectors, so the photon absorbing length is actually very large. It depends on your waveguide length, so which can be designed and fabricated. So actually for our device, it also shows better responsibility than normal instance photodetectors. And here are some more interesting comparisons. So the first one, we compare our detectivity with some other reported germanium photodetectors. So actually, our detectivity is very good compared to other germanium photodetectors which have a higher tin content. Another interesting comparison is this is the detectivity at 300K compared to other 3.5 mid-infrared photodetector. So actually, our detectivity is already better than one of the most commonly used infinity-9 photodetectors, and another PPSE photodetector. So which means our germanium photodetectors are very promising for high performance mid-infrared sensing. And another work is to develop resonance cavity enhanced photodetector. So this idea is very simple. So we just directly grow germanium PI diode structure on the SOI substrate, and the beryllium oxide layer here, because the reflective index of the beryllium oxide is very low, which is about 1.45. And the reflective index of those semiconductors are around 4. So actually, if we can grow germanium layers on a SOI substrate, we naturally form a vertical cavity. Then we fabricate a normal incidence photodetector. So from the measurement, we can see we do see some resonance peak over here. Which is due to the resonance cavity effect. And using the resonance cavity effect, we can enhance the responsibility by a factor of 2. So this is another new work about the first germanium resonant cavity enhanced photodetector. And another very interesting topic we are currently working on is flexible germanium photodetector. So for this research topic, we are collaborating with a team in Nanyang Technological University. And so after we grow germanium materials, and they do transfer printing to transfer the germanium thin film to a flexible substrate, so that you can bend it. So which can be very useful for flexible application. And there are more advantage than just transfer printing germanium to PET substrate. The first one is, as what I just said, when we grow germanium on germanium buffer, actually there is a residual compressive strain in the germanium layer, but which compressive strain is not preferred because it will increase the bandgap energy. So by transfer germanium onto PET substrate, actually we can relax the compressive strain, so we can have wider photo detection range. And another more interesting thing is strain engineering, because when we transfer printing germanium thin film on PET substrate, the structure is like this. We have a very thin germanium layer on a very thick PET substrate. The thickness of germanium is about maybe 300 nanometer, and the thickness of PET substrate is about 170 micrometer. So because it is flexible, so actually you can bend it, right? So you can feel when you bend it down on the top, actually you are giving a tensile strength to the germanium thin film, and the tensile strength will reduce the bandgap energy further, so you will push the absorption range to a longer wavelengths. And at the same time, we can enhance the we can enhance the responsibility. So from the ramen experience, actually we can see when we bend the sample with different radius, actually you can see clearly ramen shape. So which means strand has been introduced into a germinating CMP. And from our calculation, we can also see when we bend the sample, the absorption coefficient spectrum will also shift to longer wavelengths. And this figure shows the experimental measurement result on the responsivity of the device with different bending radius or strength. So using this technique, actually we can introduce 0.274% tensile strength into our device. And compared to the device without any bending, so when we can introduce tensile strength, actually we can amplify the responsivity by a factor of 3. So this is a very remarkable value. So by just bending the device, we can enhance the sensitivity by a factor of 3. And actually, we consider germinating material system may be the best platform for mid-infrared photodetector, not just only due to the CMOS compatibility and low cost, but also for the performance. So this is a Venn diagram for very special mid-infrared photodetector devices. We call it type 2 super lattice. So the idea for this structure is the factor can be very low because it is a type 2 band alignment. So the conduction band minima and valence band maxima are actually located at different positions. So the wave function, electron hole wave function overlap is very small without any bias. And when you increase bias, the electron hole wave function overlap can increase. So then they can have a very, very small curve. Okay? And for our germinating materials, actually is a very unique system. Because for our germinating material system, we, in addition to direct conduction band, we also have a indirect conduction band. And the density of state of the L conduction band is very large, which is about 8 times larger than the direct conduction band. So the optical absorption process in germinating here is when you have a photon coming in, you will excite the electron from, and you will absorb, the material will absorb the photon and excite the electron from the valence band to the conduction band. But here you can see there is a L conduction band over here. So those electrons will quickly relax to the L conduction band because the energy state is lower. Okay, and due to the momentum conservation, actually this kind of indirect band gap recombination rate is very small. So which means the lifetime is very long. So for those electrons in the direct conduction band, the lifetime is like a nanosecond. And for those electrons in the L conduction band, the lifetime is about 100 microseconds. So which means when you create electron and hole, those electrons can survive very, very long, and it will not disappear. So which means after you generate those electron and hole, you can easily collect those electron hole. So in this way, you can have a very good carrier efficiency, collection efficiency, and quantum efficiency. And another interesting thing is the tunneling effect. Because if you have electrons in the L conduction band and the hole in the valence band, actually when you give a very big bias, so actually the tunneling the tunneling chance is very small because the momentum is not conserved. So in this way, you can suppress the tunneling dark current. So typically in silicon or germanium-based photodetectors, we can see the dark current density is much smaller than 3.5 direct band gap photodetectors. Yeah, so combining the two advantage, we can have higher sensitivity, responsibility, and the lower dark current. Actually, it's possible to achieve very high performance photo detection in the mid-infrared range. And so we perform theoretical calculation to predict the performance of geometric photo detectors. So in this study, we study the performance of a normal instance geometric photo detectors with different tin content. So this figure shows the calculate responsivity spectrum with tin content from 0% to 14%. So when we increase the tin content, so we can see the cutoff wavelengths can actually shift to longer wavelengths and cover the mid-infrared range. And at the same time, the responsivity value is also increased. And when we increase the tin content, actually the bandgap energy is become smaller. So the intrinsic carrier density in the conduction band and valence band will increase as well. And after that, we calculate the diffusion dark current density. So we can see the diffusion dark current density can have different contributors from holes and electrons. But the total dark current density will increase when we increase the tin content. And when we compare the detectivity, so actually we can find that when we increase the tin content, actually the responsivity spectrum, the responsivity increase and the photo detection range increase. But at the same time, the dark current density also increase. So eventually the detectivity will drop a little bit when we increase the tin content. But we can see the detection range can cover the mid-infrared range. And when we compare the performance of geometric photo detectors with 3.5 and the in-gas photo detectors, so we can see geometric photo detectors can have better performance or comparable performance with 3.5 mid-infrared photo detectors. And so this gives us a very high promise to develop geometric mid-infrared photo detectors. And the geometric photo detectors are CMOS compatible. So you can make those detectors in a modern CMOS foundry. So the cost can be very low. Okay. Good. So here is a conclusion for my presentation today. So actually, silicon photonics has a very bright future for various applications. So actually, we can grow high-quality geometric layers by MB with tin content up to 18%. And I showed several works on different type of geometric photo detectors. And although geometric materials is very difficult to grow, but we believe this material limitation will be resolved in the near future. So SeGn geometric technology actually hold the promise for more than Moore's law. Okay, so the next slide is everyone knows Newton, right? So there is old saying about him. So if you, he said, if I have seen further than others, it's by standing up on the shoulder of giants. So if you stand on a giant or your professors or your previous group members, actually you can see farther, right? So actually we believe silicon photonics is a giant. Actually, based on silicon photonics, there are many different applications. So we believe silicon is an important technology which can help other technologies to develop better. Okay, so our research is supported by MOST, and I would also like to thank my friend and collaborator in other groups. Okay, this is my presentation. Thank you.
Okay, thanks Professor Chang for the excellent talk. So this talk is open for questions.